So let's repeat this exercise for a fluid between two parallel plates. So this fluid, the plate on top has a force applied to it parallel to the plate, and we want to know what the forces are that are set up in the fluid as a result of this applied force. First thing to note is that fluids are sticky in the sense that there is this, all real fluids have this property that results in what is called the no-slip condition, which basically is just a fancy way of saying that at solid surfaces, the fluid sticks to the surface. So fluid molecules at a solid surface, I should amend that, I should say fluid elements, not really molecules, near a solid surface have the same velocity as the surface. So if the surface is stationary, that would mean the velocity of the fluid at surface equals 0. And that is what we call the no-slip condition. That essentially says fluids do not slip past a solid surface. Locally, they stick to the solid surface. There might be velocities in the interior, but if the solid is stationary, then the fluid layer right next to that solid surface is going to be stationary. What does that mean in terms of of our analysis here? That means that once again, if we have a set of markers, we are going to have deformation as a result of that applied force, and we would repeat that same exercise which says that we can define a pressure and we can define a local deformation. The only issue here is that when we talk about a fluid, because we are applying a shear stress or a shear force, it cannot resist deformation, unlike a solid. So that means that line is going to continuously move. So there's going to be no equilibrium point where we can define an alpha. That alpha is going to keep changing as in time when we keep that force applied. So how do we define a deformation in a fluid? We can't. So what we can do is define a deformation rate. In other words, the rate at which that angle is changing. It's going to continuously change, but that rate will be constant. So we have to look not at delta beta, we have to look at delta beta, delta t, and delta A, delta t, that is the time rate of change of these quantities. And that's where the no-slip condition comes in useful, because that tells us that no matter, even if the fluid is continuously deforming, that point is going to remain fixed because the velocity here is going to remain 0. So the deformation itself, just like earlier, deformation delta A is what we need to concern ourselves with. Now, we assume that if this force F is producing a velocity u in the fluid as a result of pulling the fluid along, I would write this delta A then as u times delta t, where delta t is the time over which this delta A occurred. And the angle, strictly speaking, the angle would be delta beta, which is delta A over B. That would be U delta T over B. And the rate at which this angle is changing, the deformation rate, is delta beta over delta T, and that from here would become U over P. So we can only talk about a deformation rate in a fluid because there's no fixed deformation unlike a solid. What we are going to do now is, just like in a solid, relate this deformation rate rather than a deformation to the applied stress. So what we are going to say is that the measure of deformability here in a fluid is applied stress is tau over resulting strain, which in this case is the deformation rate, which is U over B. And in the limit of really small b, we can replace that term at the bottom with a derivative, and this expression is what we call the dynamic viscosity of the fluid. So what we have been trying to do is come up with a measure of deformability of the fluid, and that looks like it is the applied stress over the resulting deformation rate. So we are going to call that a dynamic viscosity. It's dynamic because it's the result, it quantifies forces, hence the dynamic. So this dynamic viscosity, which we call mu, is the measure of deformability, and so that's tau over U over B. And for small b tending to 0, we would replace this with some kind of derivative, and so mu becomes tau over du dy, assuming the velocity is just a function of the y direction, where this would be my coordinate. And so that really is the definition of viscosity, and this, just like the Young's modulus, is a property of the solid and relates stress to strain. Here the dynamic viscosity is a property of the fluid and it relates applied stress to resultant strain rate. So this is a property of the fluid. With the result that we have effectively defined how stresses in a fluid are related to velocities in the fluid. So I could completely rewrite this expression and say tau equals mu du dy, where this is my shear stress, this is fluid property which expresses the degree of deformability, and this is my deformation rate, we would compare this to sigma is E times epsilon for a solid. And this would be for a fluid. So these are equivalent expressions where I'm saying stress is proportional to strain for a solid and a strain rate in a fluid, and the constants of proportionality in the solid is the Young's modulus, and for the fluid is the dynamic viscosity.